Now we got to talk about energies of solution formation. One of the things that we largely ignored all of last year was that energy is associated with every single physical or chemical change in chemistry. And we've seen more energy this year, but we're going to see more of it now too. Now with solubility, the generic rule is that like dissolves like, and that's going to come back to what type of molecule and what type of solid and what type of crystal you've got. So if it's polar, it's going to be dissolved in a polar substance. A nonpolar is going to dissolve in nonpolar, and likewise a polar will not dissolve in a nonpolar and vice versa. So if we think about the solubility process and we assign some enthalpy values to this, step one, or if we say the delta H of step one, is the energy required to expand the solute particles. Okay, so we're going to take things that are closer, we're going to have to increase their kinetic energy enough to get them far away from one another. So that's step one. Excuse me, step two, or delta H2 is our second enthalpy, is going to be the expand the solvent particles. Okay, so the first, step one and step one is expanding the solute, step two is expanding the solvent. Now step three is where we're going to get excuse me, all three of these interact. So if we think of it this way, you've got delta H1, delta H2, delta H3, all combined they're going to give us delta H of the solution, or the energy associated with forming that solution or the solubility process. Alright, so steps 1 and 2 typically require energy to overcome the intermolecular forces of those molecules. So if we back up for a second, when we're talking about these things separating, in these two, you're overcoming the hydrogen bonding, the dipole-dipole, the Lindon dispersion, whatever is holding those together, that's what they're having to overcome. So steps 1 and 2 are going to require energy. It's typically endothermic. Step 3 usually releases energy. Solubility is one of those things that, again, the whole goal for atoms and molecules is to lower their energy. So even though at the beginning it's going to require a small input, step 3 usually releases energy, and that's why certain things will dissolve and why certain things won't dissolve. So step 3 is typically going to be exothermic. And again, we refer to this as the enthalpy of solution, or delta H solution. It's the sum of all the delta H values. And it can be negative or it can be positive. And typically the ones that will dissolve are going to be negative because energy is going to be released and the energy of those particles is going to be lowered. But sometimes we can force things to dissolve if we add enough energy into the system. Again, that's just rewriting the parts of the sum. Here's just our, different parts and pieces. This right here would be a scenario that was exothermic. It would have a negative delta H solution. This one right here would have a positive delta H solution. This would be endothermic. Just showing some different versions on that. Okay, so here's some example. Oil and water, which, again, sometimes you need to kind of take a step back and go, okay, what do I predict is going to happen, and then does my math make sense? Now with oil and water, we know typically they are not soluble. Right? That's why when you pull the Italian dressing out of the fridge, you have that definite line because oil is nonpolar, so it's held together by London dispersion forces. Water is polar. It's a special type of polar, so not only is it dipole-dipole, it's got hydrogen bonding. Now, it also has London dispersion and dipole-dipole, but hydrogen bonding wins, so that's really talking about what the most important force is. Delta H1 will be small. Why? Because the London dispersion forces are weak, so therefore it's not going to take much energy to separate them. Delta H2 will be large. Why? Because you're trying to overcome the hydrogen bonding, which is really strong. And delta H3 will be small since there won't be much interaction between the two. So again, the interaction is how much energy is involved for those. So the delta H of the solution will be extremely large and very positive, because the energy required by steps 1 and step 2, even though step 1 is pretty small, is going to be much larger than the amount of energy released by number 3. So that's why this one would be very large and be very positive, just looking at the types of intermolecular forces that are present. Now, sodium chloride and water. Water is excuse me, very polar. Sodium chloride is very ionic. Okay, so delta H1 will be large because ionics are some of the strongest ones that are held together. Delta H2 will be very large because you've got separating hydrogen bonding. However, Delta H3 will also be large because of the strong interaction between the ions and the water, because the ions will be positive and negative. And the water, once we get that Mickey Mouse structure, here's your negative end, here's your positive end, so you have lots of interaction. So it will be close to zero, small but actually a little bit positive. Okay, and you would have to be given values to really to be able to make this call, other than being able to recognize the forces and recognizing, excuse me, if they're strong or weak and what that would look like. But in order to make a prediction of close to zero and where it would be, you'd have to be given exact numbers on those, so don't panic too much. But so here's one of our questions here is if it's positive, then why is it so soluble in water? Dun dun dun. It's nature's what's called tendency for disorder. Look on page 517 and page 518. And although we've been talking about low energy is what everybody wants, which is true, nature also likes this increasing amount of what's called chaos, which we're going to talk a little bit about later. It's just the way it is. I can't change it. So read this if we still have questions on it, and I'll try to explain it a little bit better. Okay, so here's our enthalpy of hydration. This is still when something, hydration is just a fancy word for dissolving water, represents the enthalpy change associated with the dispersal of a gaseous solute in water. So here is our sodium chloride. Again, whenever we look at certain phases, it's just to keep everything the same. So here is our delta H1. So again, here's where I was telling you that you would have to be given actual numbers and where these would come from. Okay, excuse me. Delta H1 is 786 kilojoules. Gave us the delta H hydration. So the delta H of the solution would be the difference between those. So there you go. Here you've got remember your hydration is essentially combining delta H2 and delta H3. So in order for you to actually come up with numbers, the other ones would be having to given to you, and this is just like Hess's law. This is just showing you some energy terms for different types of solutes and solvent combinations, just so that you kind of get an idea. Polar solvents, you can have large, sums here, and just kind of looking at some of the patterns of where a solution will form, well, it won't. And even though we've just kind of told you it's all related to the molecular forces, it has more to do with the forces that are present and how it takes to overcome them. Okay, now for factors affecting solubility, you've got structure, you've got temperature, oops, where am I here? And you've got pressure. Sorry, I knew I was forgetting one. Okay, so for structure, this is kind of looking at what is present in terms of forces. So if it's hydrophobic, it's not going to like water. It's usually nonpolar. It's insoluble in water. Hydrophilic, it likes water. It's going to be polar and it's going to be soluble. And what's going to dictate that, remember, is if there is some unpaired groups on there. So here's vitamin A. It's a big long carbon chain with a ring, cyclohydrocarbon in here, and then you've only got one alcohol group, which gives us a few spots, but not enough to remember. If it's going to be soluble, it's got to surround the whole thing. So you may get some of them line up, but you're not going to get enough to dissolve the whole thing. Whereas vitamin C, every single one of these oxygen molecules, or oxygen atoms rather, if we expand that out, remember, is still going to have some lone pairs on there. So this one's going to look like this. All of the ends of the waters are going to look like this, or the ends of the alcohol groups, and then you've got your hydrogen. So all of those places where you've got oxygens and lone pairs, they're all polar. It's going to be, that's our hydrophilic, that's our hydrophobic. All right, pressure will, will increase the solubility of gases, particularly in a liquid. C is what's called concentration. P is partial pressure of the gaseous solute. Relationship between the gas pressure and concentration of dissolved gas, and the amount of gas dissolved is directly proportional to the pressure. So in other words, if there's more pressure, You can dissolve more gas. And if you just think about soda pop or a soda can, or as soon as you open that can or open that bottle, you're allowing the pressure to equalize with what's outside of it, and that's why the bubbles start to escape, because the pressure is less. Obeyed best by dilute solutions of gases that don't dissociate or react with the solvent, obviously, because if they react, they're not going to be there anymore. So the more pressure you have, the more stuff that you have dissolved. Okay, here's an example soft drink bottled at 25 degrees Celsius, contains carbon dioxide at a pressure of 5.0 atms. Assume that the pressure of the carbon dioxide in the atmosphere is 4.0 times 10 to the negative fourth atm, so much lower. What's the equilibrium concentration in soda before and after opening? K, excuse me, is a constant. It's given to us here, 32 liters times atms over moles. So you'd either be given it. Okay, now look in your book, because I got rid of the work and I didn't have time to put it back in, but it's really just plug and chug. If you look in the example 11.4, before opening the pressure is 0.16 moles per liter. After opening, it's going to be 1.2 times 10 to the negative fifth moles per liter, and that essentially, that's why your soda goes flat, is because as soon as you open it, all the bubbles escape, and then no more bubbles in your soda if you allow it to stay pressure open to the air. This is just showing you in related to temperature. You would think, dissolving a solid occurs faster at a higher temperature, so we can increase the speed if we heat it up. However, the solubility, which is the amount that can be dissolved, doesn't also always go up. For some things like sugar, like if you heat water, that's why you can dissolve a lot of sugar. That's how you make rock candy, all those. But these ones in red, and a lot of them go up, like potassium nitrate still goes up, sodium nitrate still goes up. But there are a few of them that if you increase the temperature, the solubility actually goes down. And that's like these red ones right here. And it all has to do, with the energy related to it, but we can increase the speed by heating it up, but we don't necessarily dissolve the amount, increase the amount. Kind of lied to you a little bit about that in the past. However, for gases, there is definitely a distinction. As I increase the temperature, the solubility of the gas is actually going to go down, and which really, I know seems like it would be backwards. I always think of it as if I increase the speed of those liquid particles, whatever in water, then they're moving faster, so they're just not going to be able to hold on to as much gas. I don't know if that makes sense, but that's what makes sense in my head. Again, you've got some samples there. Oops. Okay, on page 522 and 523. And I hope that helps, and good luck.